Today we are going to talk about comparing throttle position sensor signals for an electric throttle body. If you search for a diagram for an electric throttle body, one of the first hits will be a video by ADP Training, and here it depicts the following. There will be a motor that controls the butterfly valve and two sensors, TPS1 and TPS2, that are fed by reference voltage, typically 5 volts, and of course there is a ground. As the throttle opens, TPS1 sensor signal typically goes from 4.7 volts down to 0.3 volts, while TPS2 goes from 0.3 volts to around 4.7 volts. Two sensors are required for redundancy. The car computer constantly compares the measurements, and if they disagree, the car is put into a reduced power mode to prevent unintended acceleration. There can be many reasons why the sensor signals would disagree. For example, there may be an issue with potentiometer tracks wearing off. There could be an issue with connectors, corrosion in the connectors, or sometimes even coolant leaks onto the connectors. Or there can be other wiring issues such as shorts to ground or power. While sometimes the issue is obvious enough that it's visible on a scan tool, for a conclusive diagnosis, it's better to use an oscilloscope by connecting the leads to the TPS1 and TPS2 signal outputs. If we do that and command the throttle to open and close, on a properly working throttle body, we are likely to see the following picture. Channel A is TPS2, and its voltage increases as the throttle is being opened, while channel B, TPS1, is the opposite. The signals mirror each other, and that means that their sum should stay constant, being equal to the reference voltage, in our case 5 volts. But before going any further with the comparisons, first we need to check that both the signals and the reference voltage are in their expected ranges. This is something that you are likely to find in the service information. For example, you have to make sure that position sensor 1 voltage should be between about 0.3 volts and 4.7 volts, and likewise for TPS2. Also, you need to make sure that you have a constant reference voltage of 5 volts. However, when it comes to comparing the throttle sensors, often you won't find detailed information about what the comparison procedure is. So here, for example, it only talks about exceeding a predetermined value for more than 2 seconds. Sometimes you're in luck and the service information does show you how to compare the sensors. For example, here for some older Mitsubishis, you will have the following flow chart where the sum of the TPS1 and TPS2 should be between 4.5 and 5.5 volts. So how you would go around checking for that? Well, you will go to our Picoscope capture, define a channel A plus B, here it's in cyan color, and compare it to 5 volts, and it should be within half a volt here. Sometimes you get detailed information on how to compare the sensors, but it's hard to use. For example, in some Subarus, the voltage signal first is converted to angle, and then there is a whole lookup table that tells you how to do the comparison based on the throttle position sensor 1 on the y-axis and the difference between the sensors in degrees and on y-axis. Note that the allowable difference is smaller when the throttle is closed than when the throttle is open. So we've seen this already because this has a flavor of the use of the relative difference. Remember that relative difference concept was introduced to compare signals when they are in different regions. And this is pretty much what this lookup table does, only in a very custom way. So let's keep this in mind and get creative with our use of Picoscope. Returning back to the Picoscope capture, let's take a look at this A+B sine trace. We can see that it's on a scale where we cannot see much detail. So one way to deal with that would be to zoom it using the zoom tools. But I think we can do even better by the following trick. Let's use the relative difference to compare A+B with the 5-volt reference voltage. Let's just define a mesh channel to do that. I've measured my reference voltage previously and it turned out to be 5.03 volts. If you have let's say a 4-channel scope, you can just put the voltage reference on channel C and use that channel instead. But here I'm using A+B divided by 5 minus 1, and to express it in percent, I multiplied by 100. That's my scale difference for the electric throttle body with color black. It's in percent. I set the range from -10 to 10, and here we go. We have it on a scale where we clearly can see what's happening. So we see that the difference is jumping up and down when the throttle is moving, and the difference is almost flat when the throttle is constant. But in any case, the difference is between -1 and 1%, so this is pretty much the most perfect scenario. The throttle is good because it is actually new. However, if you see large spikes anywhere while the throttle is being moved or held constant, or if you let's say wiggle the wiring or something like that, or for example the difference is consistently big, then it's a reason to investigate further. One other feature of Picoscope that is going to help us with that is called the XY view. In this view, we are putting the channel A, which is TPS2, on the x-axis and the other channels on the y-axis. If everything is perfect, then TPS1, the red trace, is going to be a line with a slope -1, and the A+B line will be just a constant at 5 volts. The scales, however, do not allow to see as much detail. On the other hand, the black trace, our scale difference, gives us pretty clear picture of what's happening. And in this case, it's contained within a band of -1 to 1%, which means our throttle is perfect. If something goes wrong, then the black trace will reveal it for us. For example, if potentiometer track is worn off at a certain throttle position, then at that region we are going to see a spike in the black trace. However, if the black trace stays elevated for all throttle positions, it means that something is wrong, maybe with the wiring or corrosion on connectors or something like that. The question of how bad is too bad still remains. Unfortunately, I cannot answer this question conclusively because it differs from one car to another. For some cars, at closed throttle 6% is fine, and at open throttle 10% is fine. But for other cars, the limits can be much stricter. If the problem is intermittent, it might be possible to first establish a baseline of what's good and then compare your future experiment results against that baseline. So this comparison technique is pretty much still a work in progress, so I would really appreciate your comments, questions, and your field tests of this approach.